So today we are going to focus on providing a review of fundamental statistical concepts. And so my hope is that you will have seen virtually all of this content before in some form or fashion. Now, depending how long that's been, you may remember much or virtually none of that, and that's certainly not a problem. As compared to prior offerings of this course, I've started at a more fundamental level, so we'll have a bit more coverage of some of the basic concepts. We probably won't get as far into the most in-depth and complicated, I guess, levels of analysis here, but it should give you a very good framework in terms of your ability to apply statistical methods that are appropriate for different contexts and different types of data. So that's what we're aiming for. From a big picture perspective, one quick note, be careful that you're muting yourself so we don't have any feedback or crosstalk. And so today's lecture, we're going to focus on just 5 general topics. We'll have a high-level discussion of research and statistical inference. We'll talk about different types of variables and data that we'll be working with over the course of the semester. And then we'll review several just fundamental descriptive statistics largely, so different types of measures of central tendency, different ways we can measure variability of a data set, and then we'll wrap up with discussion of some statistical distributions. And so time permitting, we'll hopefully be able to get through all of this prior to 9:50. In the event that we don't, we can just truncate it at that point and circle back and restart with the new content on Monday. On that note, general pacing, I would anticipate on most days, I certainly won't be talking at you for the full period from 8:30 to 9:50, but it'll probably be a little bit heavier on the front end here. We'll also be using some statistical analysis packages. In the easiest case, there's some simple stuff I can show you in Excel. There's also SPSS, which you have free access to using the virtual desktop that's provided through the College of Engineering. I'll send an email with some details on that, but just keep that in mind. We'll try to do some hands-on work here as well, and you will likely be using those software programs for the purposes of the homework assignments as well. Okay, and so at the end of today's lecture, you should be able to define some fundamental concepts, including research, statistics, and several of the different parameters I had described previously. You should be able to calculate a series of those common summary statistics that would be used to provide contextual information about a data set, so mean, median, mode, standard deviation, etc. And you should also be able to standardize a variable and utilize a standard normal table. And we'll be building off of these fundamental concepts in subsequent lectures. Okay, so first and foremost, research and statistics. So when we talk about research, it's basically any scientific investigation where we're trying to establish evidence regarding some question of interest, or we would generally refer to that technically as a hypothesis. So we've got some hypothesis that we are trying to either prove or disprove, as the case may be, going into either an experiment or some other manner in which we are collecting or obtaining data, and then we're using various methods to establish some fundamental information about a phenomenon that's reflected by those data ultimately. And so when we talk about research, one of the most fundamental aspects of that is statistics. And so statistics at a very high level is simply a mathematical science pertaining to one 4-letter word. Let's be careful with the answer to this, but what 4-letter word is statistics applying to? So statistics is basically doing things with what?
Data.
4-letter word. We are...
Math.
Sorry, that was also a 4-letter word. I could tell that we were going up in flames there quickly. So that was the joys of virtual learning. So statistics is basically a mathematical science pertaining to data, okay? So with that, you can help me to fill in the blanks between these here. So when we talk about statistics, what are we doing with those data? Emma?
I don't know.
John, what do we do with data?
we're analyzing it?
Yeah, so analysis is a key part. Before we get to the analysis step, what should we probably do? How do we get the data?
Collect it?
Yeah, so first of all, collection of the data, analysis of the data. What do we do after those two steps? So we've collected the data, we've run an analysis. Somebody was
Interpret
answering, go
it.
ahead. Yeah,
Interpret
so
it.
we're going to interpret those data, and then ultimately some somewhat underlooked aspects. We also want to work on the presentation of that data. And that presentation could occur either to a very technical audience or to the general public. And depending upon the specific context, we'll want to be careful about how we present these results, and also kind of how we provide context for what those results mean. Oftentimes in statistical analysis, we see a lot of misinterpretation. So the collection and analysis may generally be sound, but sometimes we may make interpretations that aren't fully supported by the data. And we'll start to talk about a few of those things as we move forward. And then equally important is trying to present that. What I tend to find as we work through this, when you're first writing about statistics, your writing tends to be very formulaic, and I will try to break you of that habit, although it can be good in some aspects. But what you will often find is you tend to use a lot of very repetitive sentences, and it can become somewhat laborious to read 10 sentences in a page that say this variable was statistically significant at 95% confidence. So there are ways we can concisely present that data to our audience as well. Okay. All right, so a fundamental question then is, well, so why do we need statistics? If we think about this from a big picture perspective, typically we're starting with some research question of interest, and it is in many cases straightforward for us to collect data that describes that process. And then based on those data that we've collected, we'd like to be able to make some sort of definitive conclusion as to our hypothesis of interest. And so as an example, we'll start with something that's fairly easy that we should all have a good grasp on. And so let's talk about speed limits as an example. So in 2017, the state of Michigan increased speed limits on more than 900 miles of two-lane rural highways and on more than 600 miles of high-speed rural freeways. And so as a part of that, we may suspect that speeds would tend to go up as a consequence of those speed limit increases. Now, we could go out and collect data, and we've collected tens of thousands of observations to date to investigate this topic. But let's just say we were scarce in terms of our resources that we had available to us. And so we just went out and we collected speeds from 100 vehicles before the speed limits increased, 100 speeds from vehicles after the limits were increased. And we may find out in comparing those that really nothing had changed necessarily. And so that wouldn't necessarily mean that the speed limits didn't have an impact, but there are a wide range of other factors that come into play. And when we think about data, and this is particularly true in the transportation domain, we are typically dealing with data that describe the behavior of individuals, and inherently trying to predict individual behavior is extremely challenging because there are a lot of things that impact that behavior besides, for example, just speed limits in this case. So there are other factors that could affect travel speeds, weather conditions, the presence of law enforcement, the level of traffic congestion on the roadway, etc. And in the best case, we're able to explicitly account for this information. But in the transportation domain, we often find we may just have data provided to us without a lot of that contextual information. And so it can become somewhat challenging for us to be able to sort through some of that noise and uncertainty. And so the fundamental reason we need statistics is because it provides basically a series of tools that allow us to account for the variability in our data, control for that variability to an extent, and then more accurately or precisely ascertain what the impacts or differences between samples or with respect to a hypothesis of interest, what the true nature of that relationship may be. Okay. And so simply speaking, let's say we've got some variable X. We may be interested in knowing what the average value of that variable is. And so we're going to denote that mean of X as mu, as the Greek letter mu. And so let's assume, for example, that this is just the average speeds of vehicles in the state of Michigan. So we could determine what the average is based on a sample of data. And our best guess as to the speed of any given vehicle would, generally speaking, and there'll be some caveats I'll introduce subsequently, be whatever the mean speed from the sample we have to work with. But there'll be a bit of noise, a bit of variability between the speeds of individual drivers due to each of those factors I had alluded to previously. So some of it's contextual information that's somewhat separate from our general hypothesis. So in this case, whether or not the speed limit has an impact. So like weather conditions, there's really not a direct relationship between weather conditions and the decision to increase the speed limit. Now we can go into a deep rabbit hole there as to where limits are increased, but let's just table that for the time being. So we've got all these other factors that are coming into play. And so X is basically then a random variable because this is a stochastic process. We're not going to observe the same speeds every time we conduct one of those measurements. We can estimate its mean value, but we're going to find that the speeds of any individual observation or the measurement of any random variable is going to vary about that mean just purely due to randomness or noise. And that's largely accounting for other factors that influence X that tend to vary over time and space or whatever the context of our study may be. Okay. And so when we think about statistics, a few important points to consider, and a lot of times I think this kind of gets washed over to a degree, but we refer to two general types of statistical measures, or sorry, two types of measures to describe the quantities we use in this field, and those are parameters and statistics. And so when we talk about a parameter and a statistic, these are basically analogous terms. They describe similar quantities with one key difference, and I'll show you the definition right here. So when we talk about a parameter, it's a quantity such as a mean that is calculated from data and describes a population, okay? When we show the definition for statistic, it's going to be very similar, except what keyword is going to be different in that definition? Does anybody recall?
Sample?
Yeah, thank you, John and Misha. I think you're answering simultaneous there. So in the case of a statistic, we're basically a quantity such as a mean that is calculated from data and describes a sample, which is therein a subset of that broader population. Now, from our perspective as statisticians or engineers, we would prefer if we could measure the parameter directly. Now, practically speaking, there are challenges related to the costs and resources required to accurately measure the population parameter, and there are limited cases where we'd have those types of investigations. But one example that is very timely would be the US Census, for example. So in that case, we actually do try to measure every household in the United States. And as a consequence of that, it requires a lot of resources, a lot of time, a lot of personnel. And generally speaking, it's not going to be necessary for us to collect information about every unit or every observation or every person in that population. We can typically come to solid conclusions using just a subset of that data. And we'll talk later in the semester about how much data would be required in order for us to have a sufficiently large sample to answer some of these questions of interest. But what we're trying to do fundamentally is basically take that data, that information that we've collected for the sample, and we're trying to make inferences based on the entire population. And those inferences are going to be based upon whatever trends and whatever metrics we observe within the sample. And so thinking about this from a big picture perspective, then it's going to be very important for us to try to ensure to the extent possible that the sample on which we're basing our analyses and our subsequent inferences is representative of that population from which it is drawn. And there are a variety of reasons why those conditions won't necessarily hold. And we'll talk about that more as we work through the course. But if we think about the example of looking at changes in vehicle speeds, if we go out and collect speed measurements, there's various factors that are going to influence not only how fast people drive, but when they drive, and so which drivers we'd be more or less likely to observe. So if we were to conduct observations at 8 a.m. on a weekday versus 2 p.m. on a weekend, and we conducted them on different types of roadways, we would likely see significantly different trends. And so one of the most challenging aspects of statistics, particularly within the domain of transportation, is making sure that we have appropriate context and understanding of how representative that sample is of the population. Okay, and we'll talk through this in a bit greater detail in subsequent lectures, but I just want to reinforce that point at the onset. Okay, now continuing to a degree on that discussion, when we talk about designing a research study, there are several different ways we can design a study, again, aiming towards answering some research question or hypothesis of interest to us, okay? The first of those is going to be a designed experiment. This is essentially the gold standard. If you have the capability to formally design an experiment in order to answer your research question of interest, that's certainly what you should do. Oftentimes, there are reasons we can't do that, and whether those are practical or legal or ethical. Occasionally, we don't have the capability to conduct a design experiment. So as an alternative to that, we can conduct what's referred to as an observational study. Or in the, I guess, worst case, from an analysis standpoint, we could use a retrospective study. And as the name likely implies to you there, when we talk about retrospective studies, we're basically looking at going back and using historical data. And so if you think about this from a big picture standpoint, so in a design experiment, we can basically conduct a test or a series of tests where we decide which variables we would like to change. And so we can then monitor what impacts changes on those variables have on our population of interest, okay? And so if we think about that in the case of the speed limit example, we could, I guess in our best case scenario, we could just continually monitor drivers. And this is done through some naturalistic driving research that we'll talk about later on in the semester. And we could record their travel speeds before these speed limit changes went into effect, and we could record the changes in their speed after these limits went into effect. And on the basis of that information, we would be very well positioned to come to a definitive conclusion as to what the impacts of those 2017 speed limit increases would have been, okay? Now, with that being said, there are a few practical hurdles that arise in that sort of design. So part of it, it would be very expensive for us to install that equipment on all vehicles. There would probably be some privacy concerns that arose there. And this happens frequently in transportation. Oftentimes, we would like to see what the changes are of what the impacts are of a transportation policy change, or the introduction of different design or safety treatments, as a few examples there. And with those types of decisions, it's not like we can, for example, raise the speed limits, measure what the impacts are, and then go back and, if it doesn't work out the way we had hoped, change it. I mean, practically speaking, we could do that in theory, but once those speed limits have been increased, they're typically going to stay at that level, barring some unforeseen circumstances. Likewise, things like seatbelt laws, helmet use laws, things of that nature. Once you make the decision to change those policies, it becomes difficult to go back. And so for a lot of reasons, it's not going to be practical for us to design and conduct experiments formally in a transportation setting. Now, some contrast there. If we're talking about pavement design and things of that nature, where you can conduct some small scale studies, or in a driving simulator where you've got control over a lot of these factors, those would be a few examples where we can do sort of a a designed experiment, but once you put things into the real world, in addition to some of those practical challenges I had alluded to previously, we also have that noise and that randomness that's inherent in our transportation systems. And so by and large, it's going to be a very small minority of cases where we're able to use designed experiments in practice, okay? Among the most frequent that we'll see is what's referred to as an observational study. And so this is similar in many respects to a designed experiment, except we're not directly interacting with the population that we're observing. We're basically just collecting as much information as possible related both to whatever our question of interest is. So in this case, you know, we could be measuring vehicle speeds, for example, but we want to do that while introducing as little disruption as possible. So if we're collecting speed data, we probably don't want to be out in orange vests and have law enforcement there with us, because I would argue that's probably going to have at least some degree of influence. So what we'd like to do is attempt to collect as much data as feasible, while minimizing any potential impacts. And that's where some real challenges can arise when we're trying to observe behavior of individuals, because when individuals are observed, their behavior may change as a consequence of that. And so we need to basically balance, you know, the degree to which we would want to be covert and not influence those individuals with how difficult it may be to collect those data effectively, because typically the more covert we try to be, the more challenging it can be to collect that information. But in many settings, we can use observational studies as a nice alternative to a designed experiment. And in the case of the speed limit increases or the helmet law changes, there's been a bit of research that we've done after the fact to try to assess what the impacts of those policy changes have been. And in those cases, we've by and large used observational studies, essentially. Okay. And so with that being said, they are a relatively robust and rigorous study design, generally speaking, but there is some caution that should be taken because it doesn't have quite the same level of rigor, and we don't have the same level of control we would in a laboratory type experiment, for example. Okay. And then in the third case, we have what's referred to as a retrospective study. And so in this case, we're not directly observing that population or those processes in real time. We're relying on historical data from some sources that help us to describe that process. And those data have likely been archived in some form or fashion. And so if we go back to the speed limit example, in an observational study, we could have staff out in the field conducting speed measurements with LiDAR or radar guns, or cameras or various other data collection devices. From a retrospective standpoint, we've also obtained a lot of speed data of this nature as well. And typically what we're talking about here would be things like sensors or traffic counters that are installed either under the pavement or on the roadside. We've got microwave detection, which allows us to count vehicles, measure how fast they're going, etc. And so we can use that data. So from our perspective, there's not really much of a difference in terms of the underlying speed data. So we can get speed measurements for individual vehicles, for example. But the one thing that's really missing with the retrospective study is we don't have nearly as much information about the context. And does anybody care to try to elaborate on that point? So if we think about conducting speed measurements, I would be a bit more cautious about conclusions that are drawn from retrospective or historical data versus data we collected ourselves in the field. Does anybody have any insights into that? And I know some of you have been involved in the data collection, so hopefully this is an easy answer for at least a few of you in the audience. Any thoughts? So if we're just collecting data from that we've received from a vendor that's from a side-fire microwave detector or from a long-term count station, why would we potentially want to be a bit more cautious with that data than data that we've collected ourselves? Any thoughts? Asan, do you want to give it a shot here? Any ideas?
Uh, no, I don't know. What's the question? Could you please explain more?
Yeah, so let's say there's two different ways we could obtain speed data. We could get speed data from MDOT that's been collected from a permanent traffic recorder station. So basically all the vehicles going over the sensor, their speeds have been measured over time. And so we could get a report out of data from those vehicles, or we could send staff out ourselves and have one of our team members collect that same type of data. And so let's ignore the fact that the counting devices have some advantages in that they're there 24/7 and can provide continuous data. But let's say if we just conduct over a very short period, I would suggest that I would be more comfortable in analyzing the data that was collected by a person, assuming that person knows how to use the data collection equipment, versus the data that was provided to us from the count device. Any thoughts why I would feel that way?
Because of
I think.
Oh, Falarin, let's Asan can answer here, and then we'll come to
Okay.
you if you need some.
because of the device error. Yes.
So error could potentially play a role here. So calibration of those devices is a potential question of concern. I guess you could make that same argument potentially for the data collection devices that we're using, but that's a good point. Emma, I saw your hand went up. Did you have a comment to add?
I was gonna say that exact thing.
Okay. Falarin, anything else to add
Yeah,
there?
I was going to say something similar as well.
Okay. So
Device error.
okay, so device error could be one factor.
And sorry, another
Go ahead,
thing
Asa.
can be the fact that if we collect the data from the device only, we may have the data that can be not useful, so we have to filter that data, and it would be more timely, yes?
Yeah, so we could have issues with erroneous or suspect data. So you may have even values that may not necessarily make sense. Another concern that would arise there gets back to my prior point about contextual information. When we go out and we conduct the field studies ourselves, we would have relatively good information about the environment in which that data was collected. Okay, so we would know the weather conditions, the lighting conditions, the level of traffic congestion. We could get at some of this information to some degree from the permanent traffic recorders, but we wouldn't necessarily have that same level of fidelity. So when we conduct these speed measurements, one important factor is how close is each vehicle to the vehicle in front of it, because vehicles and drivers, their speeds tend to be influenced by how fast the broader traffic stream is traveling at any given time, right? And so if we're just getting readouts from a count station, we can potentially lose that information. And a consequence of that is that our speeds may be biased downwards. So we're getting lower estimates of what the actual impacts of those speed limit increases would be, because those faster drivers are constrained by the slower moving drivers, for example, okay? Weather could certainly have an impact. So I was not happy that I had to get up and shovel this morning before our 8:30 class. But if we were out driving and collecting data from a count station today, we'd probably see significantly different patterns than we would have saw yesterday, due in part to the snowfall there. Now, we could potentially get at that information by looking at historical weather data as well. But what you'll tend to find, historical weather data, you might be pulling from weather stations that are spaced 30 miles apart. And the degree to which that tells you how good or poor the pavement quality is at the time that data was collected is certainly an open question. And so for that reason, there's certainly some value in retrospective studies. But one of the biggest concerns that comes into play is simply important factors that are unobserved to us that we may know about, but we just don't have access to data that helps us to describe some of that information, or there may be important factors that we're just completely unaware of for one reason or another. So there could be some localized events. So let's say there's an emergency or a fire, or there's something that's happening near to that site that just makes things atypical on a given day. Traffic patterns are different. There could be a crash or something that's occurred either upstream or downstream. And so a lot of times we wouldn't know that information. Now, as an aside though, with retrospective data, we typically can get much larger quantities of data because a lot of that data is collected continuously. And so if we collect a very large amount of data, some of those problems kind of wash out, but most of the issues we'll talk about become particularly acute if we've got relatively small sample sizes. Okay, so as our data gets larger in terms of the quantity, some of these issues become less serious concerns. But in any case, we'll talk a little bit about each of these 3 study designs over the duration of the course. But the one big thing you want to think about as we compare these 3 different approaches is just differences in terms of the inference we can or can't draw, and then some of the hurdles that are introduced to us in trying to understand the results of those observations that we've conducted. Okay. All right, so we will continue on. So we'll be dealing with several different types of data over the course of the semester. And that includes the nature of the data. So whether it's continuous or discrete, whether it's ordinal or nominal in nature. And so just by I guess, show of hands here, you should all have the capability to raise your hands in response here. So how many of you are familiar with differences between continuous and discrete variables? Okay, I see a number of hands and or thumbs going up there. And then how many of you are familiar with differences between ordinal and nominal data? Okay, thanks. I was trying to get a general sense of what our a priori knowledge is here. And so, okay, so first of all, continuous variables. Now we've been working with data that's continuous or essentially continuous probably ever since we started doing math and or science. And so when we talk about a continuous variable, it's basically a variable where our possible values cover a range or an interval, and they can take any value within that interval, with the caveat that there'll probably be some limitation in terms of the level of fidelity or accuracy for our measurement devices. So as an example, vehicle speeds, we could probably measure to the 10th or 100th of a mile per hour in some cases, or we may be relying on a radar or LiDAR gun that's only reporting to the nearest mile per hour, for example. But it's essentially we can measure any value over that continuous range in those instances, okay? In contrast, a discrete variable is one where we have a finite number of values that can be observed, or at least a countably finite number. And so as an example, when we think about discrete variables, a lot of times this comes into play in choice situations. So in normal times, I would have driven into work today. And so there are, let's say, 3 different routes I could have generally taken. And so in that instance, there are only 3 possible outcomes as a part of that. Likewise, if we're conducting comparisons across age groups or things of that nature, anytime that our variable of interest can take only one of a limited number of values, it's discrete in nature. Now, the cut here and the distinction between continuous and discrete variables is not always cut and dry, and that relates a little bit to my prior point. So if we look at collecting speed data as an example, some of the older data collection guides that you may see would use tally sheets where you would record the speeds of vehicles, let's say in 5 mile per hour ranges. So you record whether a vehicle is going 45 to 50 miles per hour, or 50 to 55 miles per hour. And so you might have a series of 5 or 10 discrete categories there. Now you could argue that that's a continuous variable in essence, or you could argue that it's a discrete variable. I guess strictly speaking, the discrete would be more correct, but it somewhat depends upon how many of those potential values or interval we observe over that interval, essentially, okay? And so we'll talk about that more later on in the course, but depending upon whether our data is continuous or discrete, there would be different types of methods we would use to try to analyze and draw inferences from those data, okay? So the main takeaway there is that discrete variables you can count, and it's a relatively limited number of values that that variable can take, whereas a continuous variable can take a near infinite or a very large number of values if we were to try to count them over some defined range, okay? Ordinal versus nominal data really talks about the values that we're assigning to data elements. And so, for example, when we talk about ordinal data, the term ordinal simply means that we can order or rank the amount of some attribute that's possessed. So, for example, if we look at speed data, those are naturally ordered. So larger numbers are indicative of higher speeds, and that's unambiguous. So 55 miles per hour is always greater than 54 miles per hour. And there are a wide range. Most of the time when we think about data analyses, we're typically, at least in the early stages of statistical analysis courses, talking about ordinal data. In contrast, nominal data, we can apply numbering schemes or values to data elements, but there may not necessarily be any inherent meaning to that, okay? And as an example, let's say we were coding eye color. It's something that's relatively innocuous. And so we could have blue or hazel or brown or various other colors, for example, and we could number those on a 3-point or 5-point or 7-point scale. And the scale there wouldn't have any inherent meaning necessarily. So if you had blue eyes and you were coded a 3 and you had brown eyes and you were coded a 5, that doesn't mean that brown is greater in any practical sense, at least within the way I'm thinking about the data right now. And likewise, if we think about the route I take to work example previously, so I've got 3 different routes I could take. I could number those as routes 1 through 3, but there isn't necessarily any intrinsic meaning to what those numbers represent, okay? Now, there are a few cases where we tend to kind of blur the lines here a little bit. And so there are things like injury severity data. So whenever someone's involved in a traffic crash, we have a 5-point scale where we classify how severe the injuries are that a person sustained as a result of that crash. And so in that case, we could assign a value of 1 to no injury or only property damage to the vehicle. And we could have an increasing scale that goes up to 5, which would result in a fatal injury, for example. And so in that case, 5 is certainly greater than 1. So there is a meaningful interpretation there. But those data, at first glance, they would appear that they may be nominal, for example, right? But when we think about this, I guess nominal, as the name implies, oftentimes these are just labels or names for different categories of the data, whereas ordinal, there'd be some sort of natural schema that we could use to code and talk about the relative standing or relative values of those codes for the variables. Does that make sense? Okay. All right, so now we're going to do some quick recaps of some of the common measures we use to assess the central tendencies of a data set. So we're basically, whenever we're conducting statistical analyses or trying to answer research questions, we're often concerned with what the average or typical response would be. And there are several different measures we can use to try to provide some details or context as to where the center of those data lies, essentially, okay? And so first of all, the population mean and the sample mean. Now, a quick note here as I go through these measures, we talked previously about parameters versus statistics. And so whenever you see a Greek letter, as in the case of mu here, that's generally referring to a population parameter. Likewise, the capital N you see there generally means that that's the size of our entire population. So just some nomenclature there for you, as opposed to our sample mean, which is denoted here as X bar. And so in that case, since we're not with the Greek letters, we're with the Latin letters, that's indicated as a statistic as opposed to a parameter. So in this case, we would be using X bar to estimate from a sample what mu would be for the entire population, okay? And so in either of these cases, we've calculated the mean many, many times, I'm sure, over the course of our academic careers. All you're doing in this case, we've got observations, so we're measuring some variable X. That variable X is indexed to a specific observation. So here, X sub I, let's say I is subscripting. In the case of the speed measurements we talked about earlier, I may be a vehicle or I may be a driver. And there are a total of N such vehicles or drivers in the population. And so we basically add up all of those individual measurements and we divide by the associated size of that population. And that's how we arrive at our parameter of the population mean, okay? And then in the case of a sample, the approach is the exact same. We're just adding up the individual observations and dividing by, rather than the population size, the sample size in this case, okay? So you'll notice the lowercase n is denoting we're working from a sample rather than a population, okay? We'll also see the general terminology that I'm introducing here as the expected value of X. So the mean value of a sample X is generally our expected value of X. So in lieu of having any other information, if I asked you what speed you expected the next vehicle we observed would be going, your best estimate would be whatever the mean from that sample or that population would be, okay? Now, in some cases, we have statistical distributions that are skewed due to extreme outlying observations. So we may have, in the case of the speed measurements, you may have a few people that just like to drive really fast. And so they've got their car and they're just trying to see how fast they can go on a given stretch of road. And so let's say if most of the traffic's going 55 or 65 miles per hour, and then you have somebody that's going 170, that's obviously going to potentially have a major impact. What that will tend to do, it'll tend to make the mean significantly larger and it'll have more influence on that specific value than any of the other data points, just given how extreme that value is. And this is particularly a concern when we deal with smaller samples. And so as a consequence of that, as an alternative to using the mean as our best guess of the expected value or the central tendency of that data set, we can use the median. And so the median, as you're all hopefully familiar, is just whatever the middle value of that data set is, or the 50th percentile. And so, for example, let's say if we had 9 observations. So if n is equal to 9 in our sample, we would just take 9 plus 1 divided by 2 gives us 5. That just means the 5th value of those 9 would be our median, or the 50th percentile, okay? Likewise, if we had a sample size of 10, it would be our 5.5 observation, which what does that mean? We basically just take the straight line average between the 5th and 6th observations in those cases, okay? And so generally speaking, if your data are normally distributed, your mean and median will tend to be relatively close to one another, but we will run into circumstances where that's not the case. And if you have a fairly large number of extremely large or extremely small observations, the median sometimes provides a better and more representative estimate of what our expected value of an observation from that population would be, okay? And then lastly, the mode. This really becomes more useful when we're dealing with nominal data oftentimes. So this is simply going to be the value that occurs most frequently. Now, that also will tend to occur very near to the mean and the median, particularly if we're dealing with a distribution that is normal in nature. But if we are looking at the route choice example I talked about previously, so I've got 3 different routes, and let's say route 2, I take significantly more than the other. So that would be the mode in that case. So just whichever of those values occurs most frequently within our sample, okay? And so that's going to be particularly important to us, these various measures, because we are often very interested in what the mean value is within a specific data set. and how that mean value changes based upon different contextual scenarios of interest, okay? In addition to having a sense of where those data are centered or what the best representative value is, we're also very interested in knowing how much variability we would expect to see within those respective data sets, okay? And so to that end, we're interested in the population and sample variance or standard deviation, okay? And before I bring the formula up here, does anybody recall when we talk about the variance, what are we measuring? What does the variance quantify? Can anybody give that to me in, I guess, non-statistical terms, just in plain terms? So what's the variance telling us? It's telling us an average something.
The average distance from the mean.
Very close, but that's closer for the standard deviation than for the variance. So the case of the variance, it's basically our average blank deviation from the mean. This game's a lot more fun in class than it is virtually, so I'll adapt in subsequent lectures here. But when we talk about the population variance, it's basically the average squared deviation of each data point from the mean, okay? So the population variance is denoted as sigma squared, and so the way we calculate that, we take each of our individual observations, we take its difference from whatever the mean value of that population is, we square that quantity, and then we sum it for each and every observation within our population, okay? So that would give us basically the total sum of the squared deviations, and then we just divide that by the size of the population, and that converts that then to an average value, okay? Now, one interesting artifact there, then if we think back to the speed example, so we could get a number of 25 here, and then the natural question is, well, what exactly does 25 miles per hour squared mean? Okay, it's not necessarily an intuitive interpretation. And so then back, I guess, to Travis's point, we're probably more interested, rather than what the average squared deviation is, just what the average absolute deviation of each point is from the mean. And so that's what's represented by the standard deviation, okay? And so the population standard deviation, or sigma, is just the square root of that quantity that we had just talked through. The calculation is the same. We just take each point, take its difference from the mean, square it, sum those, divide by our population size, and then just simply take the square root of that measure, okay? And then as we transition to the sample variance and sample standard deviation, you will notice that the formula here are very similar in nature. The only primary differences here is that we've replaced mu by x bar, because we're not measuring the entire population, we're measuring just a subset. And so x bar is providing us with an estimate of mu, but we're not measuring mu directly. And then instead of dividing by the population size, capital N, here we're dividing by the sample size N, and we're also subtracting off 1 here for reasons we'll elaborate on the subsequent slide, I believe, here, okay? But setup's essentially the same here. These are both meant, so both the variance and the standard deviation are meant to give us a general sense of how much inherent variability there is within our data set, okay? And so if you're analyzing data of the same type that are similar in nature, we can directly compare these variances or standard deviations, but we want to be somewhat careful as we try to compare across different types of data sets. So if we compared, you know, our average travel speed to some other quantity, let's say the average commute time into work, we'd expect that those quantities would be much different, and the variability of those quantities would be much different based on a number of different factors, okay? So just be somewhat careful about that. So these values are generally informative within a sample of interest, but if we're comparing different samples or different research questions, it's tough to make inferences there. So the primary value in variance and standard deviation is just assessing the degree of variability within our population or sample of interest, okay? Now the question becomes, why the n-1 term? You've probably all been using this formula now for anywhere from, I don't know, 3 to much longer than 3 years in my case. Does anybody have any insights, or has anybody ever been explained why we have an n-1 in the denominator instead of n? Because intuitively, we're trying to estimate, you know, the variance of the population using the sample. So why would that formula not be the same? Does anybody have any thoughts? Nobody wants to jump off that diving board? Somebody wants to be really brave? Okay, I won't belabor it anymore. So there are practical and theoretical reasons for that. Now, from a practical standpoint, if we think about this, if you think back to the formula for the population and sample variances are the same with two primary exceptions. First of all, the capital N versus n-1 in the denominator. And then secondly, the inclusion of mu or x bar in the numerator, okay? Now keep in mind, x bar is meant to provide us with an unbiased estimate of what mu is in the population. And in the case of observing vehicle speeds, we probably can't observe the speed of every individual vehicle, but maybe we can sample 100 or 1,000 or 10,000 of those vehicles. And regardless of how large that sample is that mean going to be the exact same for each of those samples generally? Okay, I see some of you shaking your head not, right? So we would tend to see some variability from sample to sample, okay? And so as a consequence of that, it's unlikely that our sample mean is going to be exactly equal to what the population mean is. And so one of the implications there is we could potentially be underestimating the amount of variability that's occurring in our sample if we lose sight of that fact, okay? And now I'm going to quickly walk you through a quick theoretical example here. Now I've made this really simple, and so we're just starting. Let's assume we've got a population of 3 numbers. The numbers are 1, 2, and 3. And we're just going to do a quick experiment here. We're going to draw samples of size 2 from that population with replacement. So all that means, we're going to draw one number between 1 and 3, and then we're going to draw a second number between 1 and 3. And there are basically 9 different combinations of numbers that we could draw from that standpoint. And we'll work through and illustrate here why we want to include that correction, that n-1 term in the denominator when we're trying to calculate that sample variance, okay? And so, just as a refresher here, we're basically going to take these sample data and we're trying to obtain good estimates of what the population parameters would be for those same quantities, okay? And so we're trying to use our sample data to estimate what mu is for the population. Now, in this case, we know the entire population, it's just 3 numbers, right? And so here's a nice easy one for anybody in the audience. So what's the mean value for our population here of the numbers 1, 2, and 3? Thank you. So we've got a 2. The chat box is easier and lower stress, I think, for everyone. So I'll defer to the chat box here moving forward. And sorry, Farish, you nailed some of the contextual factors that I asked about previously. My apologies for not catching that in the chat box. You probably may think I did and was stealing all your thoughts there, but very, very good thinking on your feet there, Farish. And Falar, and I apologize, I don't have the context for what your no was in reference to there, but we're learning on the fly here. So in any case, Emma, you are correct. So if we just take 1 plus 2 plus 3, divide by our population size of 3, our mean value here is 2. And then similarly, the population variance, this should also be fairly quick and straightforward. So let's see if anybody can get this in the chat box here. So we're taking each of those numbers, differencing them from 2, squaring that quantity, summing up, and then dividing by our population size. So basically 1 minus 2 squared plus 2 minus 2 squared plus 3 minus 2 squared. And then dividing all that by 3. Very good. So Travis and Amirali, we got 2/3 is our answer there, and that is correct. So 1 squared plus 0 squared plus 1 squared gives us 2/3. And so hopefully at the end of this exercise, we will have seen that our sample variance is representative of that 2/3 number, okay? So here are the 9 different samples that we could potentially draw here. So we either get, the first number can be a 1, a 2, or a 3, and depending upon that, there are 3 other numbers that could be drawn with the second number that's sampled. And so what we're going to do, simply speaking, is we're going to take each of these individual samples, we're going to calculate what the sample mean is, and then we're going to calculate the variance using both the population formula, so dividing by n, and in this case, apologies, we're assuming that that n, whether it's capital or lowercase, is just referring to 2 in this instance. And then in the case of the sample variance, we'll take that quantity and then divide it by n minus 1, okay? And so in the first case, if our number is 1, this is a really quick and easy case here. Obviously, our mean value of that 2-number sample is 1. There's no variability, so both our variance and standard deviation, or sorry, both our population and sample variances are equal to 0. Nothing particularly informative there. As we step down to the second case, so our mean value here is 1.5. And then if we think about taking the difference of each of these from 1.5, so we would have 0.5 squared plus 0, or sorry, plus 0.5 squared when we take 1 minus 1.5, that quantity squared. And then we'd also have 0.5 squared when we take 2 minus 1.5, that quantity squared. And so then if we divide by n, which is just 2 in our case, we would just have 0.25 for that estimate, okay? If we divided by n minus 1, we would have 0.5 for the sample variance, okay? Everybody with me at this point? Or hopefully anybody with me? Okay, so continuing on, I won't go through each of these in great detail here, but if our numbers are 1 and 3, in this case, obviously our sample mean is 2, our variance using the population formula dividing by n is 1, and using the sample formula dividing by n minus 1 is just going to be twice that. So in this is our most extreme case, obviously, because we only have 2 values in our sample, and so you're never going to see differences that are any larger than this, relatively speaking. But as we continue through the exercise here, we get to the very end and we have 9 sample means, we have 9 sample variances using either of the 2 formulas, and we're just going to look at what the mean values of those respective quantities are. And you'll notice the sample mean, if we average across all 9 of those samples, gives us exactly what the population mean is, 2.0, so that's an unbiased estimator. If we use the population formula, we'll notice here we get a value of 0.33, which in this case is half as large as it should be. And so that would lead us to suggest there's half as much variability in our data set as there actually is, based upon information from our population. And if we use the n-1 formula and we average across all 9 of those samples, we arrive at the exact same 0.67 value that we've seen previously, okay? And so from a practical standpoint, we're typically dealing with sample sizes that are much larger than 2 or populations that are much larger than 3. And so as a consequence of that, you'll tend to see the differences between the population and sample variance formulas typically aren't nearly this large. And that is an exercise you can feel free to work on outside of class. But if you just take a sample size of even as little as 25 or 30, those differences start to become quite small. Now, with that being said, we should still consistently use that n-1 unless, again, you're observing every single element of that broader population. Okay? So hopefully that was an interesting exercise, something you can impress your friends and family with at your next virtual get-together. So. Okay, another fundamental term that describes the variability in our data set is what's referred to as the coefficient of variation. And so I had touched on this point a little bit earlier, and we basically have some concerns when we're comparing data that are drawn from different samples. So the variance or the standard deviation of one data set can't necessarily provide us a lot of useful information when we compare it to the variance or standard deviation of another data set, because there are inherent differences in the scales within those data sets, for example. So if we're measuring something like, I don't know, gross domestic product in the US versus speeds of individual vehicles, we'd see a big difference in terms of how variable those quantities are across observational units, for example. And so one way we can sort of normalize for that is by calculating what's referred to as our coefficient of variation. And that's simply taking our sample standard deviation and dividing by the sample mean. And so that's just telling us, as a proportion of our mean, how much average deviation we see across our sample, okay? And the next slide has just a simple example to demonstrate this. So it's continuing with the speed example. So we may have speed measurements along two roads, and our standard deviation is 4 miles per hour in one case and 5 miles per hour in the other case. And so we're simply interested in whether or not speeds are any more variable at one location or the other. And so just from looking at the data, our initial inclination would be, well, clearly they're more variable at road 5 because we see a 5 mile per hour standard deviation versus 4 miles per hour. However, when we normalize that, taking into consideration what the mean speeds are at those locations, we'll find that our coefficient of variation is actually the same here. So we can't really say definitively that there's any difference whatsoever in terms of the overall variability at speeds across those sites, at least as it compares to what the prevailing mean speeds are at those given roadway locations, okay? So just another way that we can provide some additional context to make things more of an apples to apples comparison, okay? All right, now we're going to talk a little bit about a few different statistics that help us to quantify the shape of a statistical distribution. And so we're going to introduce a little bit of additional nomenclature here. And so feel free to refer to the Washington et al. Textbook for further details here. But the data we presented previously, so the standard deviation, or the variance rather, that we presented previously is also referred to as the second moment about the mean. And we refer to it as such because we're basically taking each observation, subtracting the difference from the mean, and we're squaring it, right? There are complementary measures referred to as skewness and kurtosis, and those are referred to as the third and fourth moments about the mean, respectively. And so the first of these, skewness, is basically telling us how symmetric or asymmetric a distribution is, okay? So generally speaking, in an ideal case, our methods are easier and more robust to apply if our data are symmetric. And with a symmetric distribution, we basically find that our mean, median, and mode are equal to one another, and we have similar relative numbers of observations in each direction relative to that mean, median, or mode, okay? Our distributions start to exhibit skew when we see some observations that are outliers and are extremely high or extremely low, for example. So in this case, when we see several extremely high numbers of observations, so if our data are clustered right along these points generally, but we see a relatively large number of very large values here, and in contrast, over in this distribution, we see we also see some relatively larger numbers of very low values relative to where that distribution is centered, okay? And so depending upon where that cluster of larger values occurs, if it occurs on the right, we refer to that as right skew or positive skew, because that distribution is tending to be skewed in the positive direction. And in contrast, if those extreme values are occurring on the left side, we refer to that as a left skewed distribution or a negatively skewed distribution, okay? And so that parameter is going to be denoted as gamma 1. It's calculated as shown in the formula here. So like I said, we're just taking the difference between each value and the mean, and we're then cubing that, and then we're dividing that by sigma cubed, and all that does is convert this to a unitless measure, okay? And so the estimator for that, and apologies, I'll fix this subsequently, we should see that this is being summed from I equals 1 to n. So all we're doing down here, we're just taking each individual observation, differencing it from the sample mean, cubing it, and so that's the numerator. The denominator, we're just taking that quantity squared by the square root, and so that's basically like an s cubed term, essentially, and that gives us an estimate of skewness, okay? So if the distribution is symmetrical, we'll find that this parameter is equal to 0. Its standard deviation is roughly the square root of 6 over n. And then depending upon how far it is from 0, that tells us how symmetrical our data is. And so in short, if you're within plus or minus 1/2, we can basically, that data is essentially symmetrical for all intents and purposes. Once we get beyond 0.5 in either direction, that's when skew starts to become a concern. And particularly if we're beyond 1 or -1 in terms of that skewness parameter, those are some values that we would have some concerns with. So we have our kurtosis parameter. And so this is the fourth moment about the mean. So we're taking each observation, subtracting the mean, and then raising that to the 4th power. And what this is basically measuring is how heavy the tails are in these respective distributions. Okay, so as compared to the symmetric distribution you saw previously, in this case, we have a significantly larger number of values that are out in the extreme regions of the distribution. And in this case, we have a significantly smaller number of extreme values. And so in the case where we have excess kurtosis or more extreme values than we would expect, we refer to that as a leptokurtic distribution. And in the case where we see fewer extreme values, we refer to that as a platykurtic distribution, okay? And so keep that in mind. Our main focus here when we talk about kurtosis is on these extreme values. There's actually some ambiguity in some of the textbooks. We're not necessarily talking about how peaked the distribution is, though you will see that the leptokurtic distributions tend to have a higher peak and platykurtic have a lower peak. But if you think about how this value is calculated, as you'll see on the subsequent slide, since we're taking these differences to the 4th order, any of these values are contributing very marginally to that calculated statistic. It's these values that are the leverage points that are really going to influence this kurtosis parameter, which you see indicated here, okay? So like I said, we're taking the fourth level, 4th power difference of each individual observation from its mean, dividing by sigma to the 4th power to make that unitless. And then when we're dealing with the sample statistics, you would basically calculate those measures as shown in equation for G2 right here, okay? Now, interestingly, this kurtosis parameter, if we calculate it normally, is going to be tended to, it'll be centered around a value of 3. So if there's no evidence of excess extreme observations or fewer than expected extreme observations, we'll get a value around 3. And so as opposed to a kurtosis parameter, we'll generally work with an excess kurtosis parameter, which is just, in this case, G2 minus 3 as an example, okay? And so when we subtract off 3, it becomes advantageous to us because then the leptokurtic distributions, so the one that have more extreme values than we would expect to see, have positive values, so greater than 0. And platykurtic distributions, or those that have fewer extreme values, are going to have a negative value in that case, okay? So I will circle back and correct those slides, just the few formula errors. This is probably a good point for us to wrap up today. So I will kind of reorient myself for next Monday's lecture. And so what we'll look to do, we'll continue our discussion and our introduction to probability distributions, and we'll start talking a little bit about interval estimation. And then in the meantime, by this Friday at midnight, we've got our first 2 due dates. Now, these should hopefully not be very heavy lifts on your end. First of those, pre-course survey. Those of you that have taken courses from me before, I do this in basically all of my courses. So just getting some feedback from you about your background, your knowledge of statistics, and your familiarity with different aspects, different topics. I'm also interested in whether you have access to any data that could be used for the purposes of our term paper project. And then if you have any questions about statistics or research methods, I would be very interested in basically collating that collection of questions and hopefully coming up with answers to all of them over the course of the semester, okay? So like I said, typically the lecture shouldn't be quite this long, but I guess we had about a 5-minute late start today. And I've got a better sense of pacing. I think moving forward, I will try to use the chat box more extensively. But I'll try my best to ensure we've got interaction. It's just, it can be really challenging in this virtual environment. So does anybody have questions on anything before we wrap? We've got a whopping 2 minutes or slightly less than that. Any questions on anything?
Yeah, Dr. Salwani, could you go?
Oh, go ahead, Jordan.
Could you go back to slide 16 really quickly, possibly?
Sure. Okay, so slide 16. Your question, Jordan?
I just didn't get those ranges for the different skewness levels.
When you say you didn't get them, I went through it too fast. Is that what you're saying? Or
I think I just didn't realize that I had to copy it down because it wasn't already on the slide. Thanks. I got it now. Thank you.
Okay. Oh, and quick note there, I did upload revised slides shortly before class, so apologies if you are working from an older set, but they should hopefully be showing up. So, okay. Any other questions? Okay, if not, you all have a great day. And if you have any issues, particularly with the video upload, let me know. I'll try to troubleshoot that on the back end still, because it's not showing up exactly how I had hoped that it would show up. But I think that's just kind of a function of how D2L is structured. So, okay. All right, thanks, everybody. Have a good one.